Good morning, everyone. So today I'm going to present our recent work, TransFi. This is a joint work with my recently graduated student, Ray. So, all right. So in recent years, we have been seeing new physical layer wireless technologies being developed in both research and academia and industry. And these new technologies aims to improve the wireless network performance and enable new emerging wireless applications. So for example, when we are trying to better support delay-sensitive applications such as online gaming, people are developing new technologies that insert new physical layer preambles into the physical layer frames so that we can better coordinate between the transmitters and avoid interference. And similarly, we are talking about IoT, and whenever we are having a large amount of IoT devices that are concurrently transmitting, we are requiring more agile and fine-grained spectrum usage. So people are developing new technologies like OFDMA to achieve such a more fine-grained spectrum usage. But however, whenever we are trying to use these new technologies in practice, a common problem we're encountering is that it's hard for us to adopt this technology to the commodity devices, because if we want to do so, we always need to upgrade their hardware, and such a hardware upgrade in many cases is difficult or even infeasible. So when we're looking at the reason why such hardware upgrade is always necessary, the basic reason is that whenever we're upgrading the physical layer protocols or technologies, we are always introducing incompatibility of the signals between the old technology and the new technology. So basically, just considering if we are generating a new signal from the new technology, then basically the old hardware, the old system will never be able to produce, transmit, detect, or decode the new signals. So with that being said, the basic question that this paper is trying to answer is that how can we avoid such hardware upgrade? Because we think this is critical to practically adopt the new physical layer technologies on those large amount of commodity devices. So intuitively speaking, this is hard, right? So because this signal compatibility is inherently there. But we find out that there is a possible way to do this, which is the packet emulation. So packet emulation has been a technique that has been developed for a few years, and people have been mainly developed the packet emulation techniques for cross-technology communication. So in this simple example, I will first illustrate how this works for cross-technology communication that has been done already. So consider we're trying to transmit signal from a Wi-Fi device to a Zigbee device, right? So similar signal incompatibility is there. So if you just arbitrarily transmit the Wi-Fi signal, this can never be detected or decoded by Zigbee device. But however, we will be able to carefully articulate the Wi-Fi data payload being transmitted so that when these data payloads are being transferred to a signal, to the time domain signal on the air, the signal will closely approximate to some of the legitimate Zigbee signals. Although such approximation will never be 100% precise, but from the Zigbee's point of view, it will be able to decode it to some Zigbee data payload that we want. So however, we find out there is a major limitation of the existing packet emulation work when we are trying to use these techniques to address the hardware upgrade issue we talked before, is that most of the existing emulation, they are coarse-grained in the sense that they are using a single commodity signal to emulate another signal in another technology, but for any type of existing wireless signal, there is a limited variability, which means any existing wireless transmitter can only produce a finite type of the possible signal waveforms. So with that being said, no matter how you choose the best approximation, such approximation cannot be 100% match. And with that being said, due to this coarse granularity, the existing work are mainly focusing on emulating the control messages for coordination between different devices, such as RTS, CTS. And these messages, when you are transmitting them, they are mostly always have fixed contents, and they are always being transmitted at the lowest speed. And on the other hand, we find out that the same technique is not sufficient to emulate new physical layer technology, because in this context, our goal is trying to emulate and transmit high-speed data payloads, which may have random contents in it. So with that being said, what we are trying to do in this paper is trying to improve the emulation accuracy to another magnitude so that we are accurate enough for emulating random data payload in new signal formats. So our basic idea is that we are leveraging the MIMO capability that is widely available on today's Wi-Fi system. So instead of using a single Wi-Fi signal for emulation as existing work, we are using multiple signals being transmitted over different MIMO streams. So although if you look at any single signal that is being transmitted in one MIMO stream, there is no exact match, right? Just like the existing work. But when these signals are concurrently transmitting and mixed on the air, we will be able to achieve much better variability and granularity so that we can approximate to the target signal with much higher accuracy. And now, in order to realize this basic idea, the key question that we have to answer is how we select these multiple signals to be transmitted in different MIMO streams. And our basic rationale behind such a selection is based on the QAM modulation being used in current Wi-Fi system. So, as you can see from this figure, in QAM modulation, we can always find out the correspondence between any time domain signal and the corresponding constellation point on the complex plane. And whenever you want to manipulate the time domain signal waveform, you can easily do that by moving the signal on the complex plane. And with that being said, if we want to design the signal mixture, we want to make sure that the mixed signal match our expectation on the complex plane. We simply need to select a set of constellation points and make sure that the geometrical combination of these selected points match the target point on the complex plane. And with such rationale, we designed our system, which is TransFi. So TransFi is a purely software technique that is being designed to be operating on commodity Wi-Fi transmitters. So we use software techniques to compute the MAC layer payload being injected into the commodity Wi-Fi hardware, so that when these payloads are being transmitted over different MIMO streams, their mixed signal on the air will be able to produce the target signal we are trying to emulate. So generally speaking, the TransFi operations is trying to reverse engineer the physical layer operations on the commodity Wi-Fi device. So what we do is that we are having a target signal waveforms in mind. And as we said before, we are trying to select a set of constellation points that is being used in the commodity Wi-Fi physical layer, so that whenever these constellation points are being transmitted and mixed on the air, they produce a target signal. And in order to do this, we first translate these commodity constellation points into the corresponding physical layer payload based on the specific Wi-Fi modulation scheme being used. And then we reversely engineer the Wi-Fi encoding to translate these physical layer code words into the corresponding MAC layer payloads. These MAC layer payloads will be the output of the TransFi software, and they are being injected into the commodity Wi-Fi hardware to different MIMO streams and being transmitted on the air. And now, obviously, the key problem we have to solve first is how do we select this set of constellation points? And the tricky thing here is that if we want to make sure that such selection is optimal, then for any given target signal, there may exist multiple selections that can provide the same approximation in theory. So for example, as you can see in this simple example, there are at least 2 selections that provide the same approximation in theory. But which is the better? Which is better in practice? So we did, to answer this question, we did some measurement study, and we find out that if the signal and the constellation points you are selecting have a higher amplitude, then basically when these signals are practically transmitting on the air, they are producing larger distortion during the channel propagation. So as you can see from this example, the selection 1 with larger amplitude will produce much larger distortion when they are being transmitted. So with that being said, our criteria is that if you do have multiple selections that provide the same theoretical approximation, we always select the set with the minimum amplitude. And based on this criteria, we designed a iterative algorithm to select these constellation points one by one. So to illustrate how this algorithm works, we use a simple example that uses 64 QAM constellation points to do the emulation. And in this example, suppose we are using 4 MIMO streams for the emulation. Then we first reduce the range of selection to the set of constellation points that are closest to the target signal. After that, we start our selection with the first constellation point being selected as the closest one to the target signal. So as you can see in this example, the first one we are selecting will be D. And after that, we are considering, okay, so if the first one has been D, then if we want to precisely approximate the target signal, then ideal position of the second selection could be just computed as the reverse of the geometrical combination. So in this case, it will be the red dot position. But you can see this ideal position will never match any of the available constellation points, right? So then our second selection will be the closest constellation point to this ideal position. In this case, it will be A. And similarly, we repeat this procedure, and we will be able to make our third selection and the fourth selection. So by reducing this range of selection, then we reinforce our previous set criteria. We are always making our selection within the range of the minimum signal amplitude. And after we have selected this set of constellation points, then our next question, as we said before, is that we're going to translate the selected constellation points to the corresponding MAC layer payload so that they will be able to be injected into the commodity Wi-Fi hardware. And from here, as we said before, in order to do this reverse computation, what we did is that we are trying to reverse engineer the encoding, the physical layer encoding on commodity Wi-Fi. But here, it actually brings an additional challenge. So as we all know, the physical layer encoding commodity Wi-Fi is going through a trellis diagram, and this can be equivalently represented as multiplying an encoding matrix. And by doing so, they are appending additional parity bits to the MAC layer payloads for data correction purposes. And in a commodity Wi-Fi encoder, because we are appending extra bits, so for any given MAC payload, you can always find out the legal parits that produce a legal physical layer payload. So this can always be done. However, when we are trying to reverse this procedure so that given a physical layer payload and we are trying to compute the corresponding MAC layer payload, it's equivalent that we are pruning some bits from the given code word. So this cannot be always done, and there is a possibility that we are selecting some constellation points for emulation, but then we find out that we cannot reversely compute the corresponding MAC layer payload. So to address this issue, our solution is that before we are doing such reverse computation, we are appending some extra random bits to the physical layer payload where we choose. And in order to do so, the encoder matrix will be correspondingly expanded. So with that being said, if we carefully articulate the amount of extra random bits we are selecting, we can make sure that this encoder matrix will be always a full rank one. And under this condition, you can mathematically prove that we can always make sure that for any given MAC layer, physical layer payload, there is always existing a legal MAC layer payload that can be computed. So basically, that's the high-level design of our system. And for implementation and evaluation, we implemented our system on a Astros AR9580 commodity Wi-Fi transmitter, and we are evaluating them under different environmental settings, including regular indoor settings with different transmitter and receiver locations, and also some special indoor conditions, including a confined area, for example, under a table or in a drawer, in which you have a significant signal blockage. And we are also evaluating them on different outdoor scenarios, including a open area, a corridor, and things like that. And in our evaluations, we are picking up 3 different custom wireless physical layer technologies that are trying to produce new wireless signals in both time and frequency domains. And we are trying to see whether our technique can precisely emulate the signals that are being transmitted using these technologies. So the first one we are emulating is a CSMA-CN. This is a technique that inserts a new physical layer preamble for interference cancellation and collision detection. The second one is FSA, which is an agile spectrum usage technique, which allows a transmitter to partially utilize a 20 megahertz channel for more efficient spectrum usage. And the third one is OFDMA, and we are trying to emulate the frame structure and additional preambles being added when you are trying to use OFDMA over different users. So our basic methodology is that we emulate the preamble, and we are trying to transmit the emulated package on air, and we are then comparing the performance of this emulated package with the performance results being reported in the original paper. So as you can see in this figure, when we are emulating the custom CSMA CN preamble, we can achieve very similar level of performance compared to the original result presented in the paper. And furthermore, we are also emulating the standard Wi-Fi time domain signal, including the standard Wi-Fi preambles and the Wi-Fi data payloads. So this figure shows that we can precisely approximate to both the standard Wi-Fi preambles in different cases, and the emulation accuracy in this case, for most of the Wi-Fi preambles, can achieve higher than 90%. Then, when we are emulating Wi-Fi data payloads, even if these data payloads are being transmitted at high speed, we only need extra 1 to 1.5 dB in order to reach a very low BER, lower than 1%. And within this emulation of the time domain signal, we are also evaluating the computation and the storage overhead of doing such emulation. So as you can see from these figures, the TransFi operation in the software domain resulting only consuming a very little amount of storage overhead, and its timing being consumed will be well fit into the timing constraint of the Wi-Fi physical layer operations. So with that being said, you can safely use our technique to achieve real-time communication and the data transmission in practical cases. And furthermore, we are evaluating the performance of emulating frequency domain signals. And this figure shows that when we are trying to emulate the FSA technique to achieve agile spectrum usage, we can similarly achieve very high frame detection rate, and data payloads can also be safely transmitted with minimum errors. And at last, when we are trying to emulate OFDMA, what we did is that we are emulating the allocation of 45 data carriers being evenly distributed to 4 users. Then for each user, you will first need to emulate the specific OFDMA frame, then you transmit the data payload. So similarly, we first emulate these frame headers, then we emulate the data payloads. So this figure shows that in this emulation, we only need extra 1 dB to achieve the same level of performance in a commodity OFDMA system. So with all these results, it seems that TransFi can achieve very high emulation accuracy, but then the question is, what's the scope, right? So obviously, we never expect TransFi have magically capabilities to be able to emulate everything. So in the first place, you can see the emulation accuracy of TransFi will generally increase if you are using more MIMO streams or using higher order modulations, which brings extra variability of the signal waveforms. But on the other hand, the main limitation of the TransFi emulation is that the granularity and accuracy is basically limited and capped by the existing OFDM subcarrier spacing in a commodity Wi-Fi. So for example, in the currently being used the commodity Wi-Fi, most of the Wi-Fi systems, their subcarrier spacing is around hundreds of kilohertz, but then in some new developed Wi-Fi standards, such as Wi-Fi 6, they further reduce this spacing to a 25% of the original. Then if you have a finer spacing, we will be able to achieve higher accuracy. So to summarize, TransFi trying to develop software technique to achieve much better fine-grained emulation accuracy, and we have evaluated that this can be used to emulate different types of time domain and frequency domain signals. So I will stop here. Thank you.
Thanks.